And it's recording. Very good. Thank you for that reminder. And yes, and as someone just kind of pointed out, I will be recording all the live sessions. So if for some reason you can't make it for the 3 o'clock Wednesday, I totally understand. You'll be able to watch those later, and we'll just have to figure out another time for you to take your quiz, because I would like to do those kind of synchronously and have those together all at once. Okay, so what I'm showing here is just my public web page. So this is Tilde LS Starkey off of the Cal Poly. You'll see a link for, this is my web page. And so down here for fall 2020, I have, for the lab, I have our homepage here. Okay, so this is kind of a nice one-stop shopping because all the materials will be here. And this is normally all I use. I usually don't use Blackboard for my classes because this way it's kind of public and everyone can have access to it. But I understand, now that we're remote and we can't pass work back and forth to each other physically, that, I will be doing everything in Blackboard. But as you can see, I have not yet organized that for the entire semester. So what I have created though is I have created the schedule. This was actually my summer job, was putting together a schedule for all the sections of Chem 3150 this semester. So you can see that is put together here. So I do have a plan. I just haven't implemented that plan into Blackboard yet. So that will be coming, and I'll try and get caught up and ahead of the game. But of course, we'll at least be a week ahead. So it's coming up. Okay, but this is the schedule. And as I'm putting this together, I've kind of, perhaps you guys have experienced this a little bit too. I've kind of gone through all the stages of grief, that you experience ever since things went down in March and life got disrupted. And one of you shared in the chat room that, like, I really, I'm going to miss lab. That's my favorite part. And I'm kind of the same. You don't really miss lab until it's not there anymore. Like, oh, that was awesome, because it is exhausting. But so I'm right there with you. This is not how any of us were planning on doing this semester. The lectures we can kind of figure out one way or the other, but certainly it's the labs that are going to be a very, very different experience than we normally have. Okay, but that doesn't mean it's going to suck. That doesn't mean it's going to be a waste of time or that you're going to lose out, because in this transition, we can actually end up doing some really cool things that we would never get to do otherwise, right? There's a lot of hazardous reagents that we don't want to touch and we don't want to work with because it's just too risky or too expensive to clean up and that sort of thing. We normally come in and do just like one experiment because that's all we have time for in our short little 2-hour and 50-minute time. But now with Beyond Labs, you have a virtual lab bench, and you could do 10 experiments in 30 minutes. So we could like do a series of trials and compare and contrast and learn about reactivities. And so we could do all sorts of very interesting exercises that we normally wouldn't be able to do. And so that's the thing that I am getting very excited about. So hopefully you can kind of move forward with me with a little sense of adventure and see what we could get out of this. And I'm going to be working hard in the background, getting our worksheets ready, getting our exercises planned out to maximize, our learning outcomes and to minimize busy work, right? I don't want to do anything just because here's 10 things I want you to do, just so you have something to do this week, right? It really is about the learning outcomes. Here's what I want you to come out of this with, and that's why I'm doing this experiment and this exercise. So I've kind of come around and ended up being very optimistic and excited about it. I very much miss interacting with you guys and meeting you and getting to know you, and so that is still painful, and that I don't know if I'm ever going to get over with. But the Padlet is cool because that's a way that we can make connections. I am planning on having certain experiments be with partners, so you'll have a chance to connect and do some work and have a chance to talk about chemistry with someone, because I think that's so important. So anyway, as the semester unfolds, we'll just continue to learn new things, and eventually we'll be back together. We'll be face to face. We'll be making a mess in lab, and training our hands, because we're not getting an opportunity really to train our hands, but we can train our minds. We can do a lot with the theories and things like spectroscopy and those sorts of tools, and some of the things that maybe we've short-sighted that kind of get shortchanged rather in a traditional setting, because due to lack of time and space and all that, we can actually expand and do some cool things that you otherwise wouldn't get to. So, so with that, we'll take a look at our outline here. So I do have, let's see, there's a couple calculations that we're going to look at for next week's lab. There's a brief pre-lab for next week's lab. We're going to be looking at alcohol oxidation reactions, and we're going to do a couple of them and compare them and see how they work. And we're going to be using Beyond Labs for that. So has everyone been able to get Beyond Labs, or has anyone not checked it out yet? Or does anyone have no idea what I'm talking about? If you haven't had a chance to look at the syllabus, if there's any questions you have, you can go ahead and unmute yourself and jump in, or you can put that up there.
So if we just click on the link, it just takes us to YouTube, right? So we don't actually have to pay that $25 to download it, or do we?
No, so this is a demo. So on the ones that have the demo by Michelle Leslie, those are YouTube videos to kind of give you an overview to see how it works. But then you're going to be doing it yourself and recording your observations and answering questions about it and so on. So some of them have some demonstrations, but you're going to be doing it yourself, and we're going to be doing things beyond labs, beyond what is shown in the demo. So you're gonna be like running a reaction and following it by TLC, and so you're gonna take snapshots of the TLC, or you're gonna sketch those, and so you're gonna be following instructions that are laid out for the worksheet, and from there you'll be able to answer questions. So the $25 actually covers things beyond organic chemistry. So I don't know if you'll have a chance to do anything in physics or some other really interesting labs that they have out there. And it is for a whole year. So if there's something else that we need to do, in a different semester, because we'll probably be having a remote spring as well, as my best guess, that subscription would extend through that. But it's kind of like you're trading your lab fees this semester. So you don't have to pay for gloves, or new goggles or anything. But instead of lab fees, we're doing the Beyond Labs subscription. So I'll post that that worksheet. I don't think I've done that yet for the alcohol oxidation. I'll post the worksheet for that. I just finalized it last week, and you'll see it just kind of steps you through step by step on what to do, and you can watch Michelle's little tutorial, her overview as well, so she kind of shows you how things work. Let me see, and before we go, if we have some time at the end of today, I can show you around as well. Okay, so our first couple, our first 3 weeks actually are going to be Beyond Labs exercises. And then we're going to transition to a couple video demonstrations. We're doing a lidocaine synthesis, which actually is a lab that we have been doing in the 3150 curriculum. And so I'll get you the procedure for that. If you guys happen to have the Gilbert and Martin book from 3140 lab, then you could use that, but I'll get that procedure for you. And these are ones that we're doing more traditionally in our lab notebook, setting up for it and so on. And then we're jumping back and forth a little bit beyond the Beyond Lab and so on. At some point, we're doing a mass spectrometry. So in week 8, you can see we're doing a mass spectrometry lecture. So that's another day where we're going to be getting back and spending a longer time doing our synchronous sessions so that we can learn some new analytical tools. And there's actually some stuff you could do with spectroscopy in Beyond Labs, but I haven't. I might have a little worksheet to accompany that. And then some more lab demo videos, including some that I've prepared. And so some of these, like in week 14, that one, maybe 13 and 14, we might actually get together synchronously and watch the video together, because it has a whole bunch of embedded questions, and that way we can kind of answer those questions as they come up and have a discussion. So that's what we're going to wrap it up with at the end. And you can see week 12 has our holiday there. Okay, so we have the link here for Beyond Labs for getting that. It is something that you download to a device, so you want to think about what, laptop or something that you use most often that you can have for that. But it's asynchronous, so you could do it any day of the week that is good for you. So that's very convenient. There's also a lab notebook, lab textbook, a lab technique textbook by Lisa Nichols, and it's free. And it has great photos in it. It has great discussion of theory and so on. So if you did not already download that for $31.40, make sure you get a copy of that PDF so you have access to it. So that's a great resource if you want to, review how to do a TLC or how to run a column or how to, do a distillation or whatever technique it is we're doing each week. That's going to be a great resource for you. Okay, any questions about what the schedule looks like?
For the Beyond Labs, is there
Yes.
like a place online for us to write up the pre-lab, or is there a place for us to like send a PDF? So how do you want us to do that?
So let's see. I think I think I have that kind of written out in the syllabus. Okay, so let's look at the syllabus, and then I'll address that. And if I don't, come back, you can come back to that question. So Zoom link is here. Was that the same Zoom link that I had? Yes. Okay, I think so. Someone pointed out that I had all different Zoom links on there. My office hours. Actually, I'm doing my office hours in my personal Zoom room, which is the Zoom LS Starkey one here. And so that is a different one than our classroom. So the way I'm doing office hours this semester, I have 4 hours set aside for office hours. And what you could do is you can go to Calendly to schedule a 15-minute chunk if you want to come to office hours. Okay. That doesn't mean you only get 15 minutes. That just means I know for sure someone's going to be there at that time. So I'm, ready with my sound and the right computer and so on. And I'm not just at some other workstation. And if they're all if they're already booked up for the time you want to come, then you could just join the room at that time. So it's going to be just like our regular office hours, where if I had it in my office and someone else walked in, I say, hey, come on in and grab a seat. And then we just kind of do tag team, and we answer questions to kind of take in turns. And because a lot of times, the questions you have are going to be similar to the questions that other people have. So, so don't feel limited to it. I just want to have the scheduling system so that I'm not like sitting at my computer for 2 hours with no one showing up. That didn't work very well in the spring. So, so we're going to give that a try this semester. It worked out very well today so far. But this is also going to be the semester of being adaptable, being flexible, and kind of changing course as we move forward. So I definitely encourage you to send me feedback if something isn't working, if something you think could be done differently and would work better. Absolutely let me know so I can continue to adjust. Okay, so how we're going to do this remotely. So like I said, we're usually going to do it in class for the maybe 30 minutes every week, maybe up to an hour, depending on what we have to talk to. Certainly not 3 hours, other than today. We might be staying here for 3 hours today. So that's what we're going for. Our grading is going to have components of your lab reports, weekly lab reports, some additional problem sets. Maybe a lot of them will be spectroscopy based, so NMR problem sets and so on, or some other worksheets. We'll have pre-lab quizzes every week to encourage you to get prepared for that week's activities, and then we'll have a final at the end of the semester in week 15. So we are going to keep a lab notebook, but again, because we have divorced ourselves from the physical workspace this semester, you don't have to use your colored carbon copy paper, because you're not, copying and turning things into me. So the work you're going to be submitting is going to be as a PDF file into Gradescope. I'm going to be using Gradescope again this semester, for the first time this semester. I can't even tell you how many new technologies I'm trying out this semester. So it's like, can we have any more variables to see you know, what's gonna blow up or what's gonna be great. But actually, Gradescope is a really cool tool that that helps manage the grading, you know, which is kind of coming in from every direction. And so I'm very excited that Cal Poly invested in it and that we have access to it this year. But it's something new that we have to kind of adapt to. Maybe some of you have already worked with it. But so instead of submitting assignments through Blackboard, you're going to submit the assignments into Gradescope. Now the two are linked and synchronized. Okay, so you already have an account in Gradescope because I've already set up our course in Gradescope and synced it with the Blackboard roster. So if you go to gradescope.com and you log in with your Cal Poly credentials, it will recognize you and it should open up your 3150 lab class. Some of you might also be in my, I don't know, how many of you are in my 3150 lecture right now? You could put in the chat if you're also taking lecture right now. 1, 2, 3, 4. Yeah, we got a handful for sure. And so some people just finished it up. Awesome. So I'll look through that. Maybe it looks like maybe half of you, or a little more even, are taking 3150 this semester as well. So we'll get to know each other quite well. But anyway, I'm always going to assume that you are still in 3150 and haven't necessarily seen this material yet. Those of you who have completed the lecture course have a little bit of an advantage because you know, you've seen all the reactions, you've seen all the functional groups, so that part isn't going to be a learning curve for you. But I'll always make sure, be cognizant of the fact that you all have not finished organic chemistry yet. You're only halfway through. So we're going to be learning a lot in lecture and lab. So anyway, so some of you, when you log into Gradescope, I guess you will see both of those sections separately, whatever that interface looks like from the student point of view. And so when you log into Chem 3150 lab, you're going to see there's already a couple assignments set up. There is, are there 2 assignments? Yes, there's an NMR homework assignment that you'll be able to do after we do some reviewing today and some practice together. And then I just freshly uploaded, like 2 minutes before we started, I created a safety assignment, an emergency preparedness assignment for you to do. So there's going to be 2 assignments. They're both due next Wednesday by 3. Okay, so we're just kind of treat it like it would be a normal class where you're showing up and you could turn it in. So if you want to treat it as like, okay, Tuesday night at midnight is when it's due, so that you don't have to try and figure it out. So whenever it works for you, you can turn it in and submit it. But by that day, by our class meeting time is when I expect all the work from the previous work to be turned in. Okay, and it's going to be submitted as a PDF. So you can either, you know, if you have a tablet or an iPad or something like that, if you want to just take the assignment as a PDF and mark it up, and then just save it and resubmit it as a PDF, that's awesome. If it's something that is, you know, a free response kind of thing, then you could just you know, type it out and save it, type up a Word document and save it as a PDF. You know, that's great too. If it's some other problem where you want to print it out and you really want to work on it with pencil and paper, you know, that's fantastic too. There's a great tool called Genius Scan, which I discovered back in March. So if there's one great thing that came out of the pandemic, personally, it's me learning about Genius Scan, because I now use it like every other day in my personal life and everywhere else. So it's like anytime you have a piece of paper or a document that you want to have an electronic copy of, I use Genius Scan to take a picture of it, and it just beautifully crops it and adjusts the color and everything so that it looks like you just went to a copy machine or a scanner and literally fed it in. It's beautiful. And then you can modify it, you can make it multi-pages, you can organize your pages, and then you can send it to yourself by email, and then you have that PDF file. So so please use Genius Scan. I'll try that and see how it goes. I know there's lots of apps out there, and you can do it, you know, through whatever phone or camera settings. But what I found is that Genius Scan just always comes across as this great document versus, you know, doing it some other way with your camera. So give it a try. You might fall in love with it like I do. So lots of different ways that you can get your assignment done. And so again, now with the notebook. So if you have your old notebook and you're like, you know what, I want all my chemistry work to be in this notebook when I'm done, because I'm going to, take it with me to grad school, look back at, I still have my notebook from 30 years ago to look back at it and see my handwriting and see what I said. And it's kind of cool. So if you want to have that physical artifact and you want to keep working in the notebook you started with last semester or in first semester lab, absolutely, you can keep doing that, and with Genius Scan, you can convert it to electronic. If you want to use loose leaf paper, you could do that. Or again, if you want to say, nope, I'm staying all digital, I just want to use GoodNotes or whatever note-taking thing that I use to take notes, you can write it all down. If you just totally want to type and take screenshots, actually Beyond Labs has a digital notebook that you can use. So you could open up the digital notebook and start recording observations there. And if you want to take a snapshot of a TLC plate, it'll store it in there. So that's pretty nifty. And then of course you can export that as a PDF file that you could submit as your assignment. But otherwise, as long as you have some way of like maybe sketching, because sometimes you have a TLC plate you want to sketch or something like that. Or if you want to draw a mechanism, whatever might be part of the problem, it's nice to have the option to be able to draw like you would with a stylus. But anyway, so every week is something different. So you could try something, and then it doesn't work out, you want to try something else. Again, we're just going to be flexible. We're gonna keep trying stuff, and it's fine to modify as we go on. Okay, so I'm going to be as flexible as possible, but I think I am going to stick with Gradescope as where everything gets turned in, and that means everything has to be a PDF. So does that answer your question, or any other questions about?
I had a quick question.
Sure.
So the assignments can be found on both Blackboard and Gradescope?
So what I'm going to do in Blackboard is I'm going to use that to organize our activities week to week. And so if you look at week 1, it'll say, come to our synchronous Zoom meeting, and we're going to practice NMR. And I put out a link for, I have lectures on educator.com. If you want, let's say it's like, wow, I took first semester lab, first semester organic a year ago. I don't remember a thing about NMR. I really want to refresh on it. What you can do is you can go to my recorded lectures on that topic, and you can review those if you want. So I'll have links like that. By the way, I have the instructions in Blackboard about how to access Educator, because it's actually a commercial site. But all my students have free access, is the contract I have with Educator. So you just, it has instructions in there. Sign up for the 1-year plan and put in the word Starkey lowercase as the coupon code, and you won't have to pay for anything. So that'll actually give you all the lectures for all of organic chemistry, and I have lab topics in there as well. So anyway, back in Blackboard, I'll have, here's what we're doing this week. Here's what you need to do, that's due for the following week, work on this pre-lab or so on. And then I'll just refer to and do the homework assignment that's in and submit it to Gradescope. So like for the homework assignment, I have it as a PDF. And so that PDF you'll be able to see in Blackboard. And if you want to access it from there and print it and whatever through Blackboard, but when it comes time to submit it, you need to log into Gradescope instead and submit it there.
Okay, awesome. Thank you.
Right, and I know we're kind of juggling, and that's because on top of those 2 places, I also have my website, which it kills me to not put stuff on the website, because that's usually where I have everything organized. So certain, like today, our day 1 handouts I have up on the website, but I will not be updating the website as much. I think I'll be mostly just sticking to Blackboard and keeping the stuff in there, so I'm not trying to keep track of too many moving parts.
Okay.
All right, so weekly quizzes. Okay, so so actually this is one exception. Some of the weekly quizzes might be Blackboard quizzes. Some of them might just be a PDF that I give you when we're live, and you kind of do a written quiz and then you submit it. So it's gonna be, again, I'm gonna have to, as we move on, see what works best and see what's easiest for me and for you guys to work it out. Obviously, Blackboard quizzes have a lot of advantages because they're immediately graded, which is very nice. And, you know, you can have a window of when you take it. The problem is it's a tremendous amount of upfront work to set them up. And, you know, sometimes they're glitchy and, you know, this will be my first time using all of them. And so we don't have time to work out the kinks. So, you know, we'll play that by ear on how we're going to do either written quizzes or Blackboard quizzes. We might jump back and forth a little bit each week. So that might be the one thing that I have that's in Blackboard. And the final quiz during the last lab meeting. Okay. I also have a link here for another lab page that I have outside of our home page, and this has a link to some tutorials and some other stuff. There's just a bunch of videos I have on YouTube to review, you know, again, distillation, thin layer chromatography, all the standard techniques, recrystallization, the standard techniques that we work with. Okay. Incompletes are probably not going to be much of an problem because we're not having to miss lab. You know, it's okay if we kind of miss the synchronous sessions, but if something comes up in the semester where you can't finish the course for some reason, you know, we can work on getting an incomplete so that you can finish up at a later time. And the other really important thing to always point out, you know, in a lab course, especially when we're normally working with partners, you know, it's really encouraged that you're sharing data and working with others. And I always do encourage, in fact, joining study groups and working with partners. So if you recognize any of the names in the class and you know, looking at the Padlet, if you recognize anyone from class or someone has a common major or something, I absolutely encourage 100% reaching out and finding a partner, finding a study mate. In fact, in my lecture class, I actually offer credit for doing that, which is how much I believe in and how strongly I believe in and how important it is. So this semester, like I said, in most part, we're going to be working independently. We're not going to automatically have partners, but still, it's very easy to share data and that's encouraged, but you absolutely have to make sure that when it comes to the work that you're submitting and the work that you're doing, that it's your own work. So even if with the assignments where you are working with partners and you have shared data, and you discuss everything all the way down for all the questions, that's fantastic. But when it comes down to actually putting your pen to paper and stylus to tablet or fingers to keyboard, thumbs to whatever it is, you know what I'm saying? The metaphorical pen to paper, that you're doing your own work, right? And you know, Chegg, Course Hero, all those sites have just been the nightmare of all faculty because it's just such an easy shortcut to jump to and do that. But you know, the question you have to think, you know, I have learning objectives for this course, like I said, and that's how I ended up designing this semester. And what you have to think is, well, what are your objectives for this course, right? What do you, we're spending 15 weeks together. That's a significant amount of time. You know, wouldn't it be great if you came out of it with more than just a letter grade on your transcript, right? Wouldn't it be great if you came out of it with some skills and some insight and something that's going to help you do better when you take your biochem lab, and help you do better when you take advanced organic chemistry, and help you do better when you go out into the workplace, right? So you know, if those are your goals and those you're hoping to actually gain something from the course, then that means you're doing the work that's required. And I promise you, it will be not a huge burden week to week for your lab course. It's definitely going to be a reasonable amount of work. So hopefully you'll find, like I did when you get into this Beyond Labs virtual lab, that it's really just, it's fun. It's very interesting, and you're just kind of messing around. And if you screw up, you could just immediately throw away your stuff and start again. So it's like, you know, quick and easy. If you just trash something, you're like, oh, never mind. And then you boop, 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 let's start this reaction again and go again. So that kind of sense of exploration is really very unique, that you don't get in the real life lab. So so anyway, I hope you get as much out of the lab as you know, the time and effort that I'm putting in to make it a great experience for you. Okay, so that's our syllabus, that's our schedule. Any lingering questions that you can think of now, of course, you can reach out anytime. If questions come up along the way, you can jump in anytime, and we can address those questions as they come up. Let me see. You know what? Super quick. Let me share. I hope this doesn't screw everything up, but this is just killing me not to jump in real quick. And let me see if I can do this and share. And okay, can you see my new screen now with some pretty ski slopes in the background? All right, I see some chats here. Okay, let me just real quick go to Beyond Labs and show you what it looks like for those of you who haven't messed around with it yet. So here it is. It's literally, you know, virtual benchtop. And actually, why does it look like it's not really awake? Is anything not working? Let me restart it. It is, where are you? There you are. It's a virtual benchtop, and it's just like as messy as as a real one. So when you come in here, you could see all the different disciplines that it has, and you could download whichever one that you have. And so this is where you're downloading it to whatever machine you want, whatever device you want. Okay, and so what's cool about this too is you are working offline, and so this isn't something you have to have connectivity for. You could be at the beach or the mountains or wherever you want to go. Okay, so I'm in the organic lab, and we're mostly going to be going for synthesis. Qualitative analysis is where you could just kind of gather some spectra for anything you want. But the synthesis lab is where we're going to be spending most of our time. And so now we see we have a benchtop, and as you scroll over things, you see things happening. So we're going to be doing some alcohol oxidations. And so when I click on this, you could see the benchtop. You could see over here, all of my reagents are changing. So that's where I have all my substrates, and it'll show you these are all the things that you have available that you can work with. And so as I mouse over them, you see the little syringe that's up top here, and on the board it shows you what you're looking at. So you say, okay, I want to take this alcohol. So clicking and dragging brings the syringe over to my flask, and if you hold it in the right position, you see how it's over the center of the top. That's the rubber septum up there. So when I hold it to the top and release it, now all of a sudden you can see it's in my flask. And again, scrolling over it, you can see that it's there. So, you know, again, these are some things that kind of take some practice. Lab notebook is here. So when you click on the lab notebook, it opens it up. So this is how you can take some notes and do some things here and work on it. Let's see, we have, these are some solvents, right? So I can add in my solvent. So we'll be following instructions. So again, you have to click and drag and then release. And now I look over it and I see that I have both ether and the alcohol in here. It'll have detailed instructions stepwise for each step to have to do, but I just want to kind of give you the general idea. So if I drag it over here to my clamp, that's how I could start my reaction. And then you can, you know, bring a heating mantle over here to heat it up. This is how you would start heating it, and so on. And then anytime you want to clean things up, you bring it over to the waste container and it resets everything from scratch. So if you realize like, oh, I forgot to do this, or I screwed something up, you just drag it over here and you start again. And then once you can advance the clock here by 10 minutes at a time, or even an hour at a time. And so that's a way to kind of jumpstart ahead. And then if you, it has a lot of other cool tools. So like it has, this is a TLC chamber. So if you just drag the TLC chamber over to something, I think once it's over here and you start, if you drag it over here, it'll show you what you have. And this column is your reaction mixture. I'm sorry, this column is your starting material. And then this column is your reaction mixture. So you can keep going as the reaction progresses. Every 10 minutes or something, you can check to see what's going on. And then over on the board, it's always going to tell you what you have in your reaction. So that's cool too. And then we have an FTIR, so I could drag this over here and analyze by FTIR. I can bring over my NMR tube and immediately grab an NMR tube. I mean, look how awesome this is. I can take a melting point. After I recrystallize, I could use the melting point apparatus. Here's a mass spec if we want to take a mass spectrum. We'll learn about mass spec later in the semester. So, you know, those are some pretty cool tools that you can't do in a real lab. And I realize we also have to learn those skills of how to do each of those things in real life. But in terms of understanding the steps you would take to do a reaction and to analyze your product, you're doing all those same steps. Here's a reflux condenser if you want to heat and boil things. This is the separatory funnel. So when your reaction's done and you want to work up your reaction, I don't think it'll let me do it because I haven't like started my reaction. Like, okay, now my reaction's done. Now I want to bring it over. Now I can work up the reaction and start my extractions. And these are my solvents my workup materials I can use. Now I can add in some water and you know, take out my ether layer, or I could take out my aqueous layer and throw it out and so on. Okay, so I just wanted to give you a brief overview of kind of what the tools look like, and it is a very cool game to play. So what I'm trying to do is I'm trying to, you know, set up worksheets that will, you know, step you through, so you're not spending time like, I don't know what to do first and so on. So they will be structured experiments, but at the same time, we'll have some where it's like, okay, why don't you pick one and do another example of a Diels-Alder reaction and show what reaction you did and what product you got and so on. So so there will be some free play too in that game. Okay, so let me come back to, so any questions about let me start my broadcast from my iPad again. Any questions about how that works? Once you get your first worksheet, then you'll be able to see more detail what we're going to be doing. Oh, this is super slow. What's up with that?
Oh, Dr. Starkey?
Yeah, sure.
So I saw on syllabus it said $25 for Beyond Labs, right?
Mm-hmm.
So I downloaded it and I was able to go to the same program and everything, but I didn't pay. So what exactly are we paying for?
Oh, I think you're in demo mode. So
oh,
I
this
think
is demo mode.
I think you get something like 3 days for free, or maybe even a week for free, or something like that. So yeah, that's an
okay.
excellent point. Thank you. So everyone can go ahead and download it and start playing around with it and working with it. But yeah, at some point it's going to say, oh, demo's over. Give me some credit card information. Yeah, and so what's nice is they do give you the whole complete access in the demo mode, so you really get to see exactly how it works hands-on. So that's kind of cool. All right, so I put out the handouts for today. I'm sorry I didn't have them earlier. So if you have copies of those, you can work with those as I maybe mark up some of these things and we go through them. But what I want to do today is review IR a little bit and do lots of, and NMR as well, and do lots of examples with NMR, because I know technically you've all learned about NMR and you kind of know how it works and how to do it. But what it comes down to really solving problems, that's the challenge, and that I want to be able to work with you together and give you some strategies for attacking them so that we can work with them more efficiently moving forward. And the question is, we can leave them in demo mode until they make us pay for it. Absolutely. Yeah, unless it finally turns off at 2 p.m. on a Wednesday when your assignment's due. So, but yeah, you could. Yeah, I don't know how long the demo mode lasts, but you're free to use that as long as you can. Okay, so let's talk about IR. I don't actually, now that I'm thinking of this, I don't think I included any IR spectra in my handout. But the IR spectra, we just actually looked at one real quick in the Beyond Labs environment. So that's where we are. Let's see, I can super quick let's jump to go somewhere, and let's say IR of hexanol. Oh, I gotta love Google. Okay, so actually, this is kind of cool. The NIST web book, NAST web book is kind of a cool place to go for all sorts of spectra. But for the most part, you could just Google and immediately come up with a whole bunch of examples of things. So this is what an IR spectrum looks like, and this is where we have peaks coming down from the baseline at the top is this is transmission we're looking for. So we're looking at the IR light is passing through the sample, and if it's not absorbed by the sample, it just comes through. You get 100% transmission. So if you took an IR of nothing, it would just be a straight line all the way at the top. Okay, but at certain wave numbers, at certain frequencies, the molecule is going to instead absorb that infrared light. And so what we see is an absorption. We see that signal or that peak, and that's telling us that light has been absorbed. And so so when we look at a spectrum, oh, I just jumped, sorry. When we look at the IR spectrum, come on, show it to me. Show it to me. No reference data available. Okay, let's go back. Sorry, I jumped too far. I was trying to blow this up. That works. Okay. There we go. So as we kind of look at this from left to right, the way that I recommend kind of interpreting an IR spectrum is kind of reading it from left to right and looking for diagnostic signals. And what we're looking for is what wave number has been absorbed, and then that tells us something about a functional group. So so IR spectroscopy is all about functional group analysis. Oops, wrong button. And so this is kind of some stuff you can look for. So one thing that jumps out of this is the OH group, right? What did we see over here that tells us we have an OH? That wasn't an OH. This is not an alcohol. I could tell right away. Let's see if we have some that are alcohols. Where do we have some that look like an alcohol? What did we look for? Oh, that was a nice one down here. Nope, it went away. Where? Oh, it's not letting me get out of here. I'm in zoomed in land and I can't escape. And I dropped my iPad. That's how much I'm trapped. Oh my God. Get me out. There I am. That's a beautiful alcohol. So that's hexanol, right? And see the OH stretch, that big broad signal that's around 3,500, somewhere around there. That's our characteristic OH. So that's what I'm saying. It's like a peak you can't miss when it's available, when it's present. So we're going to look for the OH, and NHs are kind of in that same region, but they're usually much much smaller, and so they're not as common as alcohols. But sometimes we see a signal at this region, and and there shouldn't be one. Our sample is not supposed to have. It doesn't have it. It's not an alcohol. Okay, well that might be, hey, maybe your sample is wet. Maybe you didn't dry it well enough when you were doing your extraction or your crystallization, whatever. And so maybe you have a contaminant that's present. So that's something to look for too. Okay, then we're going to come to this area of 3,000. So right at 3,000 is a cutoff. If you have signals just to the left, just above 3,000, that's where we see sp2 CH bonds stretching. And literally, this is what's happening is this IR light is absorbed. That bond is stretching. It's getting longer and compressing and longer and compressing. It's stretching. And so when you have a CH that's attached to an sp2 hybridized carbon, it absorbs at a different frequency than if you have a CH that's attached to a tetrahedrocarbon, an sp3. And so so that's a great cutoff to look for the presence of double bonds. So it might be a benzene ring that has hydrogens on it. It might be an alkene that has hydrogens on it. They all kind of look the same. Okay, and then this area right below 3,000 that's where we find methyl, ethyl, propyl, butyl, you know, any other CH bond. And if we're looking at organic molecules, guess what? We almost always have CH bonds. So that's something that we can kind of recognize. Are you not going to let me? All right, let's come back to this. Oh, and now I'm sorry. It's not recognizing me if I'm not using my magic pencil. Okay, so now when we scroll through some of these spectra, if we scroll through some of these spectra, let's see if I can do this. Oh my God, I'm clicking. There we go. Just a big overview of various IR spectra. Okay, when you look at every single one of these, right below 3000, see that big long peak? So this has an OH and it has sp3ch. Right below 3000, right below 3000, right below 3000. Guess what? Almost every single molecule is going to have that because organic molecules have CH bonds in them, whether it's a tetrahedral carbon. Okay, so that's how we can look for it. But every once in a while, we'll find one where there are peaks. Here's one. This one has some absorbances in the usual place just below 3000, but then it also has some CHs just above 3000. That's our clue that we have a double bond somewhere. So again, either a benzene ring or just an alkene. All right. So we jumped to 3000. The next place to look right off the bat is in the region of around 2200. Those are usually weak signals for triple bond absorptions, where the triple bond, either an alkyne or a nitrile, is stretching. They're usually very weak, but normally that area it has no other absorbances. So when you see a signal there, it's pretty obvious that you have a triple bond. So that's kind of cool to check out. And then the other really big thing that we should never miss, a really obvious band, is when you have a carbonyl. So carbonyls can be all sorts of, aldehyde, ketone, amide, carboxylic acid. It could be all sorts of different functional groups. But the carbonyl is a very, very polar functional group. So when it stretches, it ends up absorbing a ton of IR light. So whenever you have a carbonyl, it's somewhere around the 1700 range. And it's the strongest signal in the whole spectrum. So you can't miss it. So let's see, do we have any carbonyls here? I'm guessing hexanal. Guess what? There's an aldehyde. See that huge peak around 1700? It should be one of the strongest, if not the strongest signal in the spectrum, absorbance in the spectrum. Any others jumping out here? No, because I looked for an alcohol. So here's another one. Okay, you can't miss it when it's there. This is 2-butanone, so this is a ketone. You can't miss it when it's there. If you're ever looking at a little peak here and you're like, oh, is that a carbonyl? I think that might be a carbonyl. It's not. You're wrong. Move on. Okay, you can't miss it because it's always going to be a very, very strong absorption. So the way I have this this set up, this advice for approaching an IR spectrum is just kind of glance over it, reading left to right, and picking out those really obvious bands. Look for OH, focus in right around 3000, and then look for carbonyls. Okay, because that immediately tells you some big clues about your structure. Okay, some other things we can look for: aldehydes. Aldehydes, if it's a ketone, ketone versus an aldehyde has an additional CH that's unique, and these end up as two little peaks around 2800 and 2900 that they kind of look like little vampire fangs. They're very tiny, so it's very, very easy to miss it. So let's say IR of an aldehyde. It's just a great way to get a general overview. And we'll go to images. General overview of what aldehydes look like. So here we go. See the little vampire fangs? 2850, 2750. Okay, real easy to miss, especially because that higher one very often overlaps with the other CHs, but it's going to be there. It's going to be there. Usually it's a little harder to find, to pick out, because it ends up running into the CHs. Okay, here's another one. You can only see one of the two, but the second one's there. Little vampire fangs. That's an aldehyde. That's an aldehyde. Okay, so that's something we can look for. But see what I mean? It's kind of a needle in the haystack. It's a needle in the haystack. If you look for an alkyne, kind of a less common functional group. Okay, less common functional group. But what the alkyne has is it has, if it's a terminal alkyne, it has another CH that's an sp hybridized. So if the sp3 are at 2900 and the sp2 are at 3100, then the sp3, the sp, excuse me, are going to be at a higher wave number still. So it's somewhere around 3300. Okay, but how can you look at this and know that it's not an alcohol? What is it about this peak at 3300 that makes it different from an alcohol?
Not really like long, like fat and drawn out.
Exactly. So broad is the way we describe it, right? So it's not wide; it's very narrow.
Yeah.
So you could describe this one as being sharp, right?
Yes.
Or narrow versus broad. And the OH, because of that hydrogen bonding, actually that causes that broadening. So OH signals are very unique because of their broadness, and SPCH is going to be, like an alkyne, is going to be a very, very sharp signal, but they end up in the same region. Okay, so that's a needle in the haystack you could look for as well when we're looking for those. Okay, and what else does an alkyne have? It's also going to have that peak at 2100. Notice how small it is, but always obvious, because usually there's nothing else in that region. Okay, so a terminal alkyne would have both the triple bond stretch and the alkyne CH stretch. Okay, notice I'm staying away from this messy region over here. That's called the fingerprint region. So this region, kind of 1500 and below, they call it a fingerprint because it's so complicated that it ends up being unique to a given compound. So if you take an IR and you run it through a database, software can actually match it like a fingerprint and say that you can identify a compound by IR spectroscopy if you have a computer to work on it. Okay, but as human beings go, when you're looking at these, when we look at all these different alkynes, all we could say is, okay, it's an alkyne. I don't know if it's one pentyne or hexyne or heptyne or octyne. It could be 1,000 different alkynes, and their IRs would pretty much have the same diagnostic peaks, right? So the IR is quick and cheap and easy in the lab. And so it's always an analysis that we do when we're, even in a teaching lab. It's a quick and easy analysis to do, but it's very limited in what it can tell you. Really, all it's telling you is what functional groups does it have. It doesn't give you precise structure. Okay, questions about IR? We could jump back to some other needles in the haystack we can look for. CO stretches are sometimes strong, but they're in that fingerprint region, so we can't always identify them very well. What's cool about, actually I have another table here. So this is a table that has, just a little bit of everything, not just the significant peaks. So that's when all of a sudden you turn to a correlation table and you freak out because am I trying to find everything? And the answer is no. You just pick out the important peaks and label those. Okay, but this has some nice information down here. These are for aromatic rings. Okay, for aromatic rings, benzene rings, depending on their substitution pattern, they're going to give characteristic signals in the NMR. And there's two places we can look for them. One is in this region, just to the right of 2000. You get this little pattern, and the pattern will vary depending on whether it's mono-substituted or ortho disubstituted. Ortho means that the two groups are 1,2. Meta disubstituted means the two groups are 1,3 to each other. Para disubstituted means they're on opposite ends of the benzene ring. They all give different patterns here, and they give different absorptions way down in the fingerprint region. So we can look super quick to see if I can find some. Okay, that's probably one. Do I see any obvious ones? If we jump back to our alkynes, our aldehydes, let's look at our alcohols. Oh, I didn't. Oh, sorry. Let's go to an aldehyde and our images, because I noticed this on on one of them somewhere. Okay, so this little region, am I not finding any good examples? Good examples, good examples. I picked the wrong one. Sorry about that. Come on, where are they? That one's a little too obvious. All right, so let's just say IR alcohol. Just because I don't have any examples in our handout, I'll just look at a few and see if we can analyze them. Okay, the region I'm looking for is right before things start to get super messy in the fingerprint region. I'm really not getting any examples. All right, IR aromatic. I'll just cheat. Okay, so here, look at that. It's even highlighted for us. See that little pattern, 1, 2, 3, 4? Sometimes you describe it as an aromatic ripple. That is a clue, again, kind of a needle in the haystack, but that's a clue that you have an aromatic ring, a benzene ring. We also have, that big glob over around 3000 has peaks both to the left and right of 3000. And when it's monoaromatic, monosubstituted aromatic, we're going to look way down here, this peak all the way to the far right. That might be our, the other absorption we're looking for. None of those numbers are labeled. Okay, but see, there's an aromatic ripple. There's our aromatic ripple, just that little bunch. There's our aromatic ripple. So we're seeing what it kind of looks like. Sometimes it's obscured by if you have a carbonyl. But anyway, so those are some things that we can look for that will also be evidence that we have the structure that we have. Okay, so a lot of times in our spectroscopy problem sets, there'll be combinations. So I'll give you the IR and the NMR, and that way you can use them both to try and come up with the structure. All right, let me introduce NMR a little bit, and then we'll take a break. I don't want to talk for 3 hours solid without giving you guys a break. So a couple other things in this packet of handouts, just kind of a general overview, introduction into NMR. We don't have to worry at this point about the physics of the machine and how it all works. Okay, but looking at the data that we can get from the NMR, this is where it starts getting a little overwhelming, right? Because we have, first of all, how many different signals are there in the NMR? Okay, if we're looking at a proton NMR, that tells you how many unique types of protons there are in the structure. Each one is going to give its own signal. Okay, then we can look at the integration of the signal. That's the peak area. So how big is this signal? It's the more protons you have contributing this signal, the bigger it's going to be. So a 1 hydrogen proton signal is 3 times smaller than a 3 hydrogen signal. Okay, the problem is we can't tell by our eye their relative heights because they all have different shapes. So what the computer does for us is it gives us mathematically, it measures the area and it gives us some numbers to work with. Okay, so that's how we figure out the area. Okay, the chemical shift is what we call it when we're looking at where on the spectrum, right? We look at them by ppm, parts per million. So is it, in 0 or 1 or 3, it's usually kind of 0 to 10 is the range that we're looking at for our spectra. That tells us something about its electronic environment. And then finally, the splitting pattern. So each signal can be either a singlet, or it could be split into a doublet or a triplet or a quartet and so on. And what does that tell us? That tells us how many neighboring protons it has that are different. So with all this data, this avalanche of data that comes down at us, if we get good at parsing it out and interpreting it and breaking it down, and we'll talk today about very simple ways to do that, what we could do is we could take a hugely complex structure, and from its NMR data, we can actually figure out exactly what compound we have that we're analyzing, compared to an IR, which again is like, I don't know, I have some kind of alcohol, that's a monosubstituted benzene ring. This one we say, no, you have, 2-phenyl 3-propanol or something like that. You know exactly what molecule you have. So it's a incredibly powerful tool, the ultimate tool, really, in structure determination. Okay, so I have a handout here. I'm not going to get into this in any great detail, but this talks about the coupling that happens between neighboring, non-equivalent neighboring protons, and that's what causes the splitting. Each neighbor splits the peak, and so what this handout talks a little bit about. Well, does it? Let's say I have a doublet. Is it a little bit of a doublet where the two peaks are very, very close to each other, or is it kind of a wider doublet? Is a really wide doublet? That distance between the peaks when you have splitting, that distance called a J value, or the coupling constant. And so this handout just talks a little bit about why we can have different J values, and it's measured in hertz. The typical number is kind of like 7. Pretty much every NMR that you've ever seen before, whatever distance you have between the peaks of your triplet or your quartet or something, that number, that's 7. So just for reference. So, but we could have splitting as high as 12. We could have splitting that's just 1 or 2 hertz. We get all sorts of interesting patterns that way. And we could also get some very interesting splitting patterns, like a doublet of doublets. If you have one neighbor that's a really wide splitting, and then it has a different neighbor that has a very small splitting, that's when we end up with some interesting splitting patterns. So we'll see examples of these down the road, and we'll talk more about them in detail then. I'm not sure, some of you've all come from different places and different instructors. And some people get really into NMR and do the really great, really detailed, and others are just more general. And so everyone's coming from different places. So that's why we're having an orientation today and a lesson from today, so I can get you all up to this level. And then from that, we'll jump a little higher here and there on these different topics. But I just wanted to give you some general handouts to give you some background. And then, okay, let's just look at the chemical shifts. So for the chemical shifts, we have, like I said, we kind of go from 0 ppm over here on the right up to 10 or even higher over on the left. So that's how we read a spectrum. And the reason it goes from in one place or another has to do with its electronic environment. So is it an electron rich region? Is it electron deficient region? Right, that's what we're looking at. So the ones that are further to the right, closer to 0, these are ones that are very electron rich protons. They have electron rich environments, and we describe these as being shielded. So electron rich or shielded pushes them to the right to lower ppm numbers. Okay, we also describe this region as being upfield. This is the upfield region of the spectrum. Okay, and then so when we have something, let's say like a fluorine. So if we look at, okay, we have methyl groups, ordinary alkyl groups. They come up somewhere around 1, right? So an ordinary alkyl proton comes around 1. Okay, now when you attach a halogen to it, fluorine or chlorine or something like that, and then that pulls electron density away from it because of inductive effects, right? That makes that carbon more partially positive. So that what does that do? It brings it to a higher ppm. So we see them somewhere around, I don't really have the halogens here, but right, somewhere around 2 to 4. It shifts it this way because it's a more electron rich electron deficient environment. Okay, so as we move to the left, what we find over on the higher numbers is when we have electron deficient protons. Electron deficient protons, we describe those as being de-shielded. So we say that a halogen has a de-shielding effect on that proton. And we describe this region as being downfield. So we could say that being attached to an oxygen de-shields that proton and moves it downfield, meaning to a higher ppm. Now, as an undergrad myself, this kind of broke my brain because it seemed counterintuitive, like down should be a lower number and up should be a higher number. So that always was very confusing to me. So here's what I did. I pictured underneath the spectrum, I pictured this little triangle, this little wedge. And as soon as I did that, my life just got so much easier. I'm all about mnemonic devices. So what does that mean? That means as I move from, towards lower numbers, where am I going? I'm going up this ramp. I'm going upfield. Okay, so this is going upfield, and moving from left to right is going downfield. And once I did that, that terminology kind of helped. So, so this is, I'm not gonna have a vocabulary test, but it's good to know the language, because you'll hear this terminology as you're working through the material. Okay, so let's look at some different types of protons. If you, like I said, if you have an ordinary alkyl type proton, it comes in the region around 1.5. If you are next to some kind of pi bond, if you're next to a pi bond, so you're either allylic to an alkene, or you're alpha to a carbonyl, or you're benzylic next to a benzene ring. AR represents an aromatic ring, like a benzene ring. Notice what that does. It shifts it down to maybe around 2.2 instead of 1. We're now around 2.2. Okay. Being attached to something that is very electronegative is going to have a big shift. The one that we're going to see the most often, what's really common, we're going to see oxygen so often in our structures. So that, because oxygen is so electronegative, that has a huge deshielding effect, and it brings it all the way down to 3.8. Okay, so anytime you see a proton where that carbon is attached to an oxygen, really obvious, because it's going to be one of the most furthest protons downfield. Okay, being on a double bond, now being on a double bond, vinyl, that brings it in the region of 5 or so. And then being aromatic, being on a benzene ring, brings it to the region around 7. Okay, so those are, so aromatic is all the way down at 7. And the only ones that are higher than that are an aldehyde proton, which comes around 10, and a carboxylic acid, which comes even higher. Okay, so this is just kind of a general table that lets you know where things fall. You will always have access to this table when you're working on NMR problems. I will always give you this table for a quiz or the lab file or that side of thing. So you can get comfortable working with it and using it. These are not things you have to memorize. Okay, protons on oxygen or nitrogen. So these are all CHs on the left-hand column. On the right-hand column is when you have a proton that's either an OH or an NH. And now again, we get back to this exchangeable nature, this hydrogen bonding. And because of that, the peaks kind of become more broad, like we saw in the IR. They become more broad, and they also become a lot more variable. So an alcohol proton, it can be anywhere, like 0 to 5. It depends on the concentration and the solvent you're using and maybe the temperature. So we never know exactly where it's going to show up, but very often it's kind of broad. So we could write that it's like a broad singlet. It usually does not couple either because of that exchangeable nature and that hydrogen bonding. So it usually always comes out as a singlet. And it's sometimes very broad, or sometimes it's not a big lump, but it's not very often sharp. It could be sharp, but sometimes it's more it's a little lumpier. And carboxylic acids come way downfield, so they're even higher than 10. Those are the ones that are further downfield. Okay, and so that's a general thing for that. And then it turns out that you can actually even calculate about where the chemical shift is going to be. So this is a table that will help us do some calculations, because maybe I don't have just one chlorine attached. Maybe I have 2 chlorine atoms attached. Well, what's going to happen is that first chlorine is going to pull it from 1 to 2, and then the second chlorine is going to pull it from 2 to 3. So these effects are additive. And so that first table is good if all you have is one functional group. But if you have 2 functional groups attached to a certain carbon, then we could use a table like this to estimate what the chemical shift is going to be. So for a CH2, A CH2 has 2 groups attached. So what we're going to do is we're going to start at 1.2 as our baseline position, and then we're going to move it for the 2 groups that are attached. And we could use this table to find our delta values on what we're going to, how we're going to move it, right? So things like an oxygen has a big, 2 or even 3 as a shift that it's going to do. Being next to a benzene ring shifts it downfield. Being next to a carbonyl shifts it downfield, and so on. So for example, when we look at this proton, and we want to estimate where its chemical shift is going to be. Now this is a CH. A CH starts at 1.5, and then there's 3 groups attached that are going to modify it. Okay, so for an aromatic ring, a benzene ring, where do we find that? That's right here. So that's 1.4 is what we're going to adjust for that. The methyl group is just an ordinary R group, which actually has no impact on the chemical shift. And then this oxygen, turns out that there's a lot of different kinds of oxygens. All of these are oxygens. And so what we could look is more carefully at, well, what kind of functional group is that oxygen? And we could get a more precise number to do our adjustment. So when we look here, we see that this is an ester. This is an oxygen that's part of an ester. And so we look right here. That's exactly, we have an oxygen that's part of an ester. And so that's going to have a bigger deshielding effect than, let's say, just an alcohol or an ether. So we add all these numbers up. We start at 1.5, and then we shift at 1.4 for the benzene ring and 2.8 for the ester. And so we actually can estimate it's all the way down at 5.7. That's where we would find, normally like vinyl protons. But this is an ordinary CH, but because it has those 2 functional groups, it moves it way down. Okay, so I don't know if you've used tables like this before, but I think it's just a great tool to have so that you're not trying to have to guess where the proton's going to be. You could actually have concrete tools to help you really come up with a precise number. Okay, so massive overview of proton NMR, and thinking about the chemical shifts and so on. Let's take a quick break here to give you guys a chance to stretch your legs, grab a drink, use the bathroom, whatever you want. Let's just take a 5-minute break, and then we'll regroup. I'm going to go get some water myself. If you guys want to chat and say hi, that would be cool. Let me see if I can find a timer. All right, we'll get 5 minutes after I can find a timer. Do I have a timer? Do I have a timer like I have on my watch? There it is. And let's just count down from 5 minutes. And that's how we know how long our break is. All right, go take a break, stretch your legs. Hello. Uh-oh. My iPad froze again. There we go. Okay, hello again. So someone asked on there are a couple questions here. So there is no lab manual to purchase. So I'll be providing all of the handouts and worksheets and everything and experimental procedures. So you don't have to buy a textbook. You don't have to buy a notebook, anything like that. It's just the Beyond Labs, and then everything else will be provided. And then the free PDF is just techniques based. It doesn't have experiments in it. So that's where you get the background for it. And oh, how's the kitten? Okay, now you're gonna have to share a picture of the kitten because that's pretty awesome. And you're getting a taste for what it's like to be a mom. Oh, fostering a kitten. Okay, and let's see. Any other question? Are we ending today at 5:50? Hopefully before then, because I don't want to keep you longer than I need, needed. But the key is I want to try and get as much practice as possible working on NMR problems so that you're ready to launch on your own. And you might say, oh my God, I'm a pro at NMR problems. I don't need this. And you're free to leave or watch the recording later or something like that. But before we do that, I will, let me show you one other assignment that we have for today. The one that I said that I uploaded, I realized I haven't shown you that. So let me see if I can, let me see, am I sharing my screen? I don't think I'm sharing my screen. Am I sharing my screen? I don't think so.
No.
Okay, let me come back here. All right, share screen. Let's pick this screen and let's share it. So my iPad quit on me. And can you see it now?
Yes.
Okay, thank you. So if we go to Blackboard, and here's our lab. And if you don't make this wide enough, It hides the little side window. So here's our little navigational thing. So I haven't added much here. The announcements I'll always post, and that's how I'll communicate with you primarily. So make sure you're checking your Cal Poly email or getting them forwarded to your email of choice. And so the weekly activities, this is what I will be organizing. All this stuff is kind of hidden for now. The only one you guys will see is this first one. Sorry, we're looking at my point of view. Looks a little different than yours. So here are the handouts that we are looking through today. Here's that Padlet link. So please share on that if you have not already. The homework, NMR homework assignment, I have a PDF attached here. So there's just 2 NMR problems, okay, that are similar to the ones that we're working on today. And then the other one that I did here, oh shoot, I didn't attach that file. Okay, let me go to our course homepage. I just uploaded it there instead. Nope, nope. Let's go here and here. And if you don't see, make sure you refresh the page because a lot of times I'll edit it and it'll bring up your cached version. So here's your emergency kit assignment. So good news is you're being spared the dreadful, 30 minutes of here's what we do in an emergency and here's the safety procedures and don't pipette by mouth and blah, 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 that you guys have probably heard 100 times already. But again, this is a great opportunity to say, okay, well, let's talk about safety and being prepared for an emergency outside of the classroom laboratory, because we should all have those preparation plans in place. So this is going to be the second assignment that you have this week is thinking about emergency preparedness. I have a couple websites that you can go and explore if you want more information. I have some scenarios here to consider, some emergencies that you might find yourself in that are down the line. And then the assignment is through Gradescope. When you log into Gradescope, you'll see the questions related to this are going to be in Gradescope. And so what I want you to do is I want you to review your family's emergency plan. So if you're living at home, what is the emergency plan that your family has? If you don't have an emergency plan, now is the time to create one. Okay, if you're living with roommates or something like that, then what's the emergency plan that you guys have together? Or if you have family that's close by, it's a good time to check in with your family and think about these things. So what do you do to receive emergency alerts or warnings if there's a major earthquake or fire or something like that in your area? There's Alert OC, there's other ones. What services do you have set up? What's your evacuation route? So if you're at home, how do you get out if there's a fire, let's say? If you're at your workplace, if you are, if you have to evacuate your neighborhood, you know how to get out and so on, okay? What's your communication plan that you have with your family? So how do you get in touch with each other in an emergency and so on? And what does your emergency preparedness kit look like? So if you are like me, where it's like, oh, that emergency kit, that is really something I gotta do someday. Today's the day. This week is the week. So put together an emergency kit. All those websites have like checklists of things that you should put together. Put together emergency kit. You should have one for your house. You should have one for your car. And maybe you already have one, but take an inventory of it. See if something's missing. See if you can refresh some of the items in it. And so I'm gonna ask for a snapshot of that when you do your assignment in Gradescope. One of the questions will have a file upload, so I want to see a picture of your emergency kit. And each of these is just kind of a free response thing about what did I do, what do I have planned, what's going on. And this week I really thought about how to get in touch with people. Let's say I didn't have my cell phone, how would I get in touch with the people that I would need to get in touch with, because that's the only place I have my contact information. So that reminded me I really need to print this out and have a hard copy somewhere, keep it in my wallet, whatever, right? So this is the week for you to think globally about emergency preparedness for earthquake, fire. The CDC has a great website about preparing for the zombie pandemic. because guess what? All the things you would do to prepare for a zombie pandemic, a zombie apocalypse rather, is the same stuff you would do in the case of an earthquake. So yeah, why not prepare for that as well? Okay, so you can work on that this week and then turn it in anytime by Wednesday at 3 o'clock next week, and you'll find it in Gradescope. Okay, any questions about our emergency preparedness homework? Emergency preparedness homework. All right, let's jump back to our broadcast from my iPad, if it will cooperate. It looks like it's cooperating. Fantastic. All right, let me adjust my windows again so I could keep an eye on the chat in case. And so the homepage, yeah, I just posted it there, but I meant to do it in Blackboard. I don't think I uploaded it yet. So I'll have that in Blackboard as well. And then the assignment will be in Gradescope. Okay, so let's take a look at solving some NMRs. Now, C13 is another evaluation tool we can use. So we can look at the protons in a structure, or we can look at the carbon atoms. Much less data that comes out of a C13 because we don't have that rich, splitting information and so on. But it still can be useful even without a table. So just looking at a C13 NMR, even without having a table handy, you could kind of get some information. If you have most of your signals are going to come below 100, and that's where you have your ordinary alkyl groups, right? Methyl, ethyl, propyl, butyl, just sp3 hybridized carbon, and we get the same effect when you have, something like an electronegative oxygen atom attached. It's going to shift it downfield, so you're going to have it at a higher ppm. Notice our ppms are quite different now. It's on a scale of 0 to over 200, so it's a much wider range that we're looking at. So we have sp3 carbons are here. When you see peaks that are in the 100s or so, that's where we have our sp2 carbons. So again, alkene or aromatic ring. And then all the way up around 200 is where we have carbonyls. So just a quick glance at C13 NMR, you could right away pick out, oh, I see a carbonyl, right? Maybe you don't have the IR data, but you can, that will give you a clue to your structure. Okay. Notice that carboxylic acid derivatives, usually like amides, esters, and hydrides, those kinds of things, come to the right, to a little lower number below 200, while aldehydes and ketones are usually a little above 200. Okay, so just very general data from the C13. All right, so let's dig in. Let's talk about how do we take in all this information and actually develop, come up with a structure based on just on a proton NMR. We can come up with a structure. Okay, now the problem with NMR is there's so much data. I'm sorry, I was scrambling during my break. I never got a chance to fill my water. There's so much data, it's easy to get information overload and to just have it all come in and spend an hour and get nowhere. Has anyone, show of hands, no one has their video on, but how many of you have had that experience where you felt like you worked on an NMR for an hour and at the end you still didn't have the structure? Yes, I see some claps, some hands. So I've been there too. It's crazy. So when I started teaching this, second semester organic lab, second quarter organic lab is when we taught NMR in the past. Every single student, I would give an NMR assignment, and every single student, one at a time, would come to my office hours like, I don't know what, just give me their spectrum. Like, I don't know where to start. And I would start saying, okay, well, here's how I would start. And I would say, well, let's do this first. Let's do this second. And then finally I said, what would be a good idea? How about I put this together in a handout and kind of share that with the students from the beginning as saying, here is an approach you can use to solving NMR problems. Okay. Is this the only way to solve NMR problems? Of course not. If you're already great at solving NMR problems, then you don't need to listen to anything I'm saying. Okay. But the point is, you want to have a systematic approach. You want to have, like, here's what I'm going to do, step 1, step 2, step 3, so that you keep making progress and you're not just wasting your time, spinning your wheels. All right. So here's the approach that I suggest. So first off, if you're given an IR spectrum, now we don't always have an IR spectrum. but a lot of the problem sets I'm going to give you come with NMR, proton and carbon NMR and an IR. So if you're lucky enough to have an IR spectrum, check to see if you have any functional group, what functional groups are present, right? Do that check that we said. Are there any OH groups? Are there sp2CHs? Are there any carbonyls, right? So right off the bat, that's going to give you clues to the pieces of your puzzle. Okay, now step 2, if you're lucky enough to have a molecular formula, what can you learn from the molecular formula before you even start working on the NMR? Okay, I will always give you, almost always, when you get to mass spec, we'll learn kind of maybe some tools on how to come up with a formula. But I will always give you a formula with your NMR. Okay, so what does the formula tell you? Well, there is the one thing you have to memorize. There's not much you have to memorize in organic chemistry, but one of the things to memorize is the formula for a saturated alkane. What does that mean? The saturated alkane means it has the maximum number of hydrogen atoms that it can have, not a single one more. And what that formula is, for every N carbon atom, you can have 2N plus 2 hydrogen atoms. Okay, now we have to adjust that formula slightly if you happen to have nitrogens. Every nitrogen brings with it an extra hydrogen that's required. And so really the formula is 2N plus 2 plus the number of nitrogens. Okay, and that's the saturated formula. Now when you compare that to the actual formula, and you notice that any hydrogens are missing, every 2 hydrogens that are missing we describe as a degree of unsaturation. What does that mean? Every degree of unsaturation tells you you either have a pi bond in your structure or a ring. That's a huge clue to your answer that you're trying to come up with, is knowing how many rings and pi bonds that you have. Okay, so 4 is kind of a magic number for degrees of unsaturation, because if you ever have 4 or more degrees of unsaturation, that means you might have a benzene ring, because a benzene ring has what? 3 pi bonds and a ring. So that one structural unit takes care of by itself 4 degrees of unsaturation, and it's very hard to do that otherwise without using that benzene unit. So that's really handy to consider. Okay, so work with the IR, work with the molecular formula, and of course we're going to be doing lots of examples of these in just a minute. So I'll kind of go through the steps and then we'll be applying it. Okay, so then the next thing that I always do is I go right to the peak integration. So remember that peak integration is the area under each curve and tells you how many protons are contributing to that signal. So sometimes the peak integration is given to you right off the bat. This is a 1H signal, this is a 3H signal, and so on. Other times it's given to you numerically or graphically, and then we have to interpret that information to come up with the integration. So we'll look at examples of both of those. But once you have the integration and you know how many hydrogens correspond to each signal, we're going to use that to develop puzzle pieces. Okay, so every time I see a 3 hydrogen signal, that tells me I probably have a methyl group in my structure. I have a CH3. Every 2 hydrogen signal is a CH2. Every 1 hydrogen signal is probably a CH. It could be an OH, right? Maybe you can see from your formula and from your IR if you have an OH. Maybe it's an OH. Even more rarely, maybe it's an NH, but it's probably a CH or an OH. Okay, sometimes you have some messy signals. There's 6 hydrogens, 4 hydrogens. Okay, well, a 6 hydrogen signal actually is quite possible, because maybe you have 2 methyl groups that are equivalent, right? If they're both attached to the same carbon and you can exchange them by rotation, then they show up as a single signal with an integration of 6. Okay, but sometimes you have ugly things where they're overlapping and you can't see things beautifully. So that's a possibility too. Okay, so we're just going to be using the peak integration to list the pieces. This is the step number 1, is list the pieces of your your structure. The only time I'm going to pay at all attention to the chemical shift, so I don't care where it is on the spectrum, all I'm looking at is the integration at this point. The only exception to that is I'm going to look at the region around 7 parts per million. I'm going to look at that region around 7 because I know that's where aromatic protons show up. So if I have signals around 7, that tells me I have a benzene ring. So what I'm going to do is I'm going to gather up the integration of all the signals in that region. I'm going to say, how many total aromatic protons do I have? Okay, and if they add up to 5, if I have a total of 5 aromatic protons, that tells me that I have a monosubstituted benzene ring. So what does that mean? A monosubstituted benzene ring means I have this as one of the pieces of my structure. And how many aromatic protons would this yield in the NMR? Do you see how it would give 5 hydrogens? Right? If I have one group attached to the benzene ring, that means the other positions are all protons. So this would end up giving a total of 5 signals all in that region. So maybe they're split up. There's a 2 and a 2 and a 1, or there's a 3 and a 2, or they're all together as a 5. They could be split up, but as a group, we're going to see that there's 5 protons altogether. Okay, what if I have 4 protons in the aromatic region? That tells me I have a di-substituted ring. A di-substituted ring. Okay, now what is, there's some different possibilities. It could be ortho. Okay, ortho means that my 2 groups are right next to each other. So that's the ortho arrangement. Meta means that my 2 groups are 1,3 to each other. So I don't know what those groups are, but I have something attached at the 1,3 positions. Para means that they're opposite each other. I have a 1,4 di-substituted benzene ring. Okay, but all of those would have in common, every one of these would have a total of 4 protons showing up around 7. Okay, so those are my pieces. So I'm going to start by just listing my pieces, and then the next thing I check is, do I have all the pieces? So what I could do is add them up. So far I have this many carbons, this many hydrogens. Do they compare to the molecular formula, right? My molecular formula says there's 6 carbons. If I only have 5 carbons in my list so far, I'm missing a piece. Have you accounted for the degrees of unsaturation? I said there must be a pi bond or a ring. I have to have that as one of my puzzle pieces. Okay, do they match the functional groups in the IR? So if I saw that nice big broad stretch in the IR for an OH group, that's one of my puzzle pieces. I could write it down right off the bat that I have an OH. Okay, so once I determine that yes, in fact, I have all my pieces and they're consistent with all the data I have so far, the IR, the degrees of unsaturation, okay, now we're ready to assemble. That's our last step. Okay, so what I'm going to do is I'm going to start with an N group, something like a methyl group. And I'm going to say, okay, what is that methyl group attached to? So now I look at all my other pieces. I say, well, what could it be attached to? Now I'm going to look at the chemical shift. Where on the spectrum is that? That's going to tell me maybe if I'm attached to a oxygen, right? Or a carbonyl or something like that. I'm going to look at the splitting pattern. What does the splitting pattern tell me? How many neighbors I have. Right? This is the N+1 rule. The N+1 rule. If I have 1 neighbor, what is that? What kind of splitting does that give me? It makes a doublet. N+1. If I have 2 neighbors, I have +1. I have 3 peaks. It's going to be a triplet. Right? So that's what the N+1 rule means, that if I have 2 neighbors, it's going to be 3 peaks, meaning a triplet. This is N, and this is N+1. So I use the N+1 rule to decide which other pieces I'm attached to. So slowly but surely, we start attaching pieces together and come up with bigger chunks, and then eventually we have these 2 or 3 big chunks where there's only one way to put them together, and that's our answer. Okay, so we're gonna build our structure that way, and then here's the last step that we never want to forget. Okay, is when we're done, we think we have the right answer, then we're going to check that answer and make sure it's consistent. So we're going to confirm, does it match all the data in the IR? Do I really have the right formula? Did I accidentally add in an extra carbon or forget to include one of my pieces? Okay, does it correspond with the NMR? So what we're going to do is we're going to just look at our structure and predict what the NMR would look like, and then we can compare that the 2 actually match. Okay, because if we skip this step, it's very easy to have the wrong answer and not know it. So that's what's really cool about NMR is you know when you have the right answer and you get pat on your back and you get to sleep at night, right? You also know when you have the wrong answer and you have to step back and say, well, wait, what mistake did I make? Because I know this doesn't match the data. I know it's wrong. Okay, so once you get some practice and you get good at it and you have a systematic approach, it can be a fun experience. It could be something that is not painful because you're solving a puzzle, you know, and you're figuring out how they fit together, and that's pretty cool. Okay, so I don't know if we'll get there today, but eventually, hopefully. There were many times when I got to when I got to the point with my second semester lab students, and I would hand out this week's NMR problem set, something like this that's on the screen right now. There would be a ton of the students would just immediately jump in and start solving it, and many of them would have them done, you know, in 10 minutes. So it can be a fun intellectual exercise, but we'll get there, baby steps, right? Okay. All right, so here's a typical problem set. So I have IR data, proton NMR, and then C13 NMR. I have the formula shown here. Okay, so how do I get, again, information overload, right? Right? Are some of you breaking out in a sweat right now? Let's try and resist that response. Let's see if we can have an alternate response. Okay, so what's step one? Step one is let's work with the IR. Do you see anything from the IR? Okay, what we're going to do is we're just going to kind of read it from left to right like we would read a sentence. Read it from left to right. What are we going to look for first? Any OH? No OH. Right? And then what do we look at? We jump right here to 3,000. This is the 3,000 mark. Do we have anything above 3,000? Right above 3,000, that's empty, right? Do we have anything below 3,000? We do. Okay, so we're going to label this. So these right below 3,000, these are CH bonds, but they're sp3 CHs. Sorry, I could blow this up. So I would label this as an sp3 CH. There's no sp2 CH, and there's no alcohol. Okay, we continue reading left to right. Anything else jump out at you that's significant? You could chat, you could unmute yourself.
The carbonyl.
Carbonyl, where do you see that?
Around 1,700. Around
1,700. So here's my 1,700 mark, and sure enough, big, strong absorption, strongest signal in the whole NMR, IR. You can't miss it. You can't miss it. So definitely, this has a carbonyl as well. So, so that's what I can get from the data. All this, blah, 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 who cares? I can't, that's the fingerprint region. We're not, IR is not about picking every single peak and trying to analyze it. It's just what are the significant functional groups? Okay, so that's step one. What's step two? What's step two? We want to work with our formula. We want to work with our formula. So our formula is C5H10. So the way we determine the degrees of unsaturation is, again, my approach, the simplest approach, I think, is to ask, well, if it was saturated, what would the formula be? Okay, we have 5 carbons. We have 5 carbons. So how many hydrogens can that hold? Remember, it's CnH to the 2n plus 2. That's the only formula we have to memorize for this. So 5 carbons can handle how many hydrogens? 10, and then 2 more. Yeah, I see that in chat. Very good. 12 hydrogens. So that's our saturated formula. So all we have to do is compare that to our actual formula. Our actual formula is C5H10. Okay, now it turns out that the oxygen atoms can be completely ignored for our degree of unsaturation calculation. They have no impact on our rings and pi bonds. So all we do is compare these two, and we see there's 2 hydrogens missing. That's it. No crazy formula, no plus minus, divide by 2, blah, blah, blah. we just compare the two, we see how many are missing, and for every 2 missing hydrogens, is what we describe as a degree of unsaturation. 1 degree of unsaturation. So that tells me I must have a pi bond or I must have a ring. Okay, and in fact, I already know what is accounting for that degree of unsaturation. Does anyone else already know what it is? Because the IR also pointed to something that has a degree of unsaturation. Our carbonyl has a pi bond in it, right? So just spoiler alert, we already know that that's the only pi bond in the whole structure because we have exactly 1, and there can't be any rings in the structure. Okay, so we're off to a good start. We got some data from the IR, we got some data from the formula. Okay, now we're going to jump to the NMR. We're going to dive into the NMR. And we're lucky in this case because the NMR actually already has the integration calculated for us. So the data here above each signal, it tells us how many protons are contributing to that. Okay, so what we're going to do is, and I want to see this in your work, that the homework that you're doing this week, that is not how you spell pieces. I don't know what that was. Sorry. I'm going to start by listing the pieces in my molecule. Okay, and I'm going to use the integration for that. So here's how it goes. I have a 3 hydrogen signal. What does that mean? That means part of my structure is a CH3, is a methyl group. Okay, and I'm putting 1 arm on it because a methyl group has to be attached to something, right, to be complete. Every carbon in the end, I promise, every carbon is going to have 4 bonds, exactly 4 bonds. So a methyl group is one of my pieces. What's another piece? Signal B tells me I have a CH2 also in my structure. Okay, CH2 has 2 arms because that would give a total of 4 bonds. What other pieces do you get from the NMR? Signal C is another CH2. Signal D is another CH3. Okay, so this is what's telling me about all the protons that are in my structure. These are the pieces of the puzzle that contain hydrogen atoms. That's it. Okay, so go through the integration and convert those into puzzle pieces. Okay, but before I start assembling, what comes next? Before I start assembling, I have to check to make sure I have all my puzzle pieces before I start hooking them together, right? And so what do? I check with my formula and I check with my IR to make sure I have everything. So the IR, what's missing? I know there's a carbonyl in the structure, right? So let's draw a carbonyl. How many arms does a carbonyl have? Every carbonyl is attached to 2 other things to get a total of 4 bonds. Excellent. Any other pieces? There's one more piece that's missing. How about your formula? Needs to be C5H10O2, and I only have 1 oxygen shown right now. The carbons work out, the hydrogens work out, but I'm missing an oxygen. So that's another piece to my puzzle. That's another piece to my puzzle. Okay, so notice I'm not attaching anything first yet. I'm just listing them out as individual pieces. Okay, now that I see these are adding up to C5, just a little reminder of what we did here. They add up to C5H10O2. The IR spectrum checks out with it, and my degrees of unsaturation checks out, right? Now I'm confident that I have all my pieces. Now I'm ready to put them together. Okay, so how do I begin to put them together? What I do is I start with an end piece. One of my end pieces are the methyl groups. So I start with a methyl group. Doesn't matter which one, I have 2 of them, right? I have A as a methyl and D as a methyl. Okay, but we'll start with any one of them. Let's start with D. Let's start with that one. Okay, and let's try and figure out what it's attached to. Now I'm going to pay attention to the chemical shift. Now I'm going to pay attention to the shape. I don't care up till now that it was a singlet or double or triplet. Okay, but now I'm going to look, and what do you see here? 1, 2, 3, right? That's a triplet. Triplet typically has a 1 to 2 to 1 ratio of its 3 peaks. And so what does a triplet mean? That tells us you have how many neighbors? 2 neighbors. So n plus 1, you add 1 to get the peaks, which means you subtract 1 to get the neighbors, right? So yeah, it has 2 neighbors. So who is it attached to? It must be attached to one of these CH2s that we have. I noticed someone asked about the ACS exam. Absolutely. NMR spectroscopy is on ACS. And it's on the GRE too. If you're lucky enough to take the chemistry GRE, you can expect some NMR. But very, very simple, basic NMR. Okay, so I promise you, after this semester, with the practice we're going to get with spectroscopy, you will knock it out of the ballpark. The ACS, yes, on the summer ACS. All right. Okay, so now I've attached. I've taken the methyl group and I've attached it to a CH2 group, so I can kind of mark off my puzzle pieces as they start coming together. And then I can look at this CH2 now, and I say, okay, well, what's this CH2 attached to? And I have to decide, well, is this CH2? The CH2 could either be signal B or signal C. So which one do you think? Signal B is a triplet. Signal C is 1, 2, 3, 4, 5, 6. It's called a sextet. What do you think? Could this be proton B? Could this be proton B? Would this be a triplet? If you apply the n plus 1 rule, what do you see?
I don't understand what the 6 peaks mean. Like, what does that mean again?
The number of peaks tells us how many neighbors you have. And the rule is that for an n number of neighbors, you have n plus 1 peaks. So 6 peaks means you go backwards, you have 5 neighbors. Okay, a triplet means you have how many neighbors?
2.
If you have 3 peaks, exactly, you must have 2 neighbors. Okay, so this CH2 has at least 3 neighbors, so it's going to have at least 4 peaks. It can't be a triplet. A triplet means you only have 2 neighbors. Okay, so this must be peak C. This must be peak C. Okay, and then we figure out what it's attached to. Now, what are my choices? Let's think about what's here. What are my choices? I have another CH2 group. I have a CH3 group. Can I attach a CH3 group right here? There's a problem with attaching a CH3 right here. What's the problem? I just finished my molecule, right? I can't attach an N piece yet because I have all these other pieces that still have to go in. So it's not time for an N piece. So I can't do a methyl, but it could be attached to a CH2 or a carbonyl or an oxygen. Those are my choices. See, by having the pieces listed out, I know exactly what my options are. I'm not starting with a blank slate. I just have pieces that I need to move around. So which piece fits here? That's consistent with the fact that it's at 1.6 and it's a sextet. What's the piece that must fit there? If I have 6 peaks, I must have 5 total neighbors. 5 total neighbors. So it's the other CH2 group that's attached. It's the other CH2 group. Very nice. Okay, so now, again, that needs another bond to get 4 bonds for this carbon. So this CH2 must be B. That's my other CH2. So what is he attached to? Again, my choices. It could be attached to the carbonyl or it could be attached to the oxygen. Attached to the carbonyl or attached to the oxygen. How am I going to decide? I look at B and I see where it is. What's its chemical shift? It's coming around 2.3. So is that consistent with being alpha to a carbonyl or alpha to an oxygen atom at 2.3? Let's jump back. Oh, look at this. I could do this very easily. So being next to a carbonyl, where does that bring you? What range does that bring you? That's right here, 2.2 or so. Being next to an oxygen, where does that bring you? Bam, 3.8. 3.8. Huge, huge downfield shift by being attached to an oxygen. Okay, so let's look at where we are. Where are we? We are at 2.3. So is it attached to an oxygen? No way, not. It's not far. It would be all the way down here. I actually can see who's attached to the oxygen. It's not B. So what does that mean it's attached to? What are my other choices?
Carbonyl.
Must be the carbonyl. And then at some point you get to a place where there's only one other way we can attach the rest of these groups, right? There's only one other way that we can attach the rest of the pieces. And that's having the oxygen followed by the CH3. Okay, so we assemble our pieces, and then when they assemble, that's where we have to look at chemical shift and splitting pattern. Those both have to make sense by who it's attached to. So, last step, very last step, before we move on and pat ourselves on the back, what do we have to check? Does it make sense? Did I come up with the right structure? Or did I make a mistake along the way? Okay, and this is the very last step that I want you to do. Is what I want you to do is I want you to, and this is what, if we don't have office hours where you're coming to me with a piece of paper anymore, but if you came to me and we worked on this in office hours, what I would do is I would slap a Post-it note over the spectrum. Okay, so we could do that this way. So what I'm going to do is I'm going to hide the spectrum. I'm going to get rid of the spectrum. Stop looking at the data and just look at your answer, and now predict what your spectrum would look like. Okay, you can't do it with them both visible, because here's what you're going to do. You're going to kind of force one onto the other. And even if they don't really match, you're going to say, ah, yeah, that matches. Okay, so ignore the spectrum and now look at the structure and predict the spectrum. So let's start over here on the right. So this CH3 group on the far right, it's going to be a 3-hydrogen signal. It's going to be a 3-hydrogen signal. What's its splitting pattern going to be? How many neighbors does it have? What we're looking at are proton neighbors. So
0.
0 neighbors, right? So what does that mean for a splitting pattern?
Singlet.
It's going to be a singlet. So I'm expecting this to be a 3-hydrogen singlet. S for singlet. And where is it going to be? What's its chemical shift? Attached to oxygen? Bam, 3.8. So I'm going to predict what my spectrum should look like. Tell me about the CH2 that's next to the carbonyl. Tell me about the CH2 next to the carbonyl. How many hydrogens? That's called its integration. That's called its integration. So it's going to be a 2-hydrogen signal. What about its splitting pattern? Singlet, doublet, triplet, quartet?
A triplet.
Triplet, because how many neighbors?
2.
2 neighbors. So what I'm doing is I'm looking at the attached carbons. Whoa, sorry. I'm looking at the attached carbons. These are my neighboring carbons. And I'm totaling up how many protons are on those carbons. So it has only 2 protons over here. 2 plus 1, n plus 1 means it's going to be a triplet. So I have a 2-hydrogen triplet, and tell me its chemical shift. We can come back to our table for that. Alpha to a carbonyl, 2.2. All right, the next CH2 has a total of how many neighbors? Has 3 over here and 2 over here. It has 5 neighbors. It has 5 neighbors total. Okay, now The Klein textbook does not do a good job on this particular part of the concept, so I don't know how much you relied on Klein versus the lecture from your 3140 instructor. But what we're going to do is we're going to add all those up because they all have the same J value. This is a freely rotating molecule. They all have a J of about 7. So we just look at them as, so even though the CH2 is not the exact same as the CH3, all 5 protons are exerting the same coupling on the CH2. So with 5 neighbors, we expect 6 signals, six peaks. So this is going to be a 2 hydrogen sextet is what we call it. There's no abbreviation for that. We spell it out. A 2 hydrogen sextet. And where is it going to be? Where's an ordinary CH2 group? An ordinary CH2 group, just right here, just plain old CH2 1.3. Just picking a number. 1.3. Nope. Okay, this last one. What is this last methyl group going to be? Integration is 3. Splitting is triplet. Chemical shift for a methyl group on our table, something like 0.9, just somewhere around 1.
Dr. Stark,
Yes.
I have a question.
Sure.
So is the integration number always going to be given?
We'll look at some data where we'll look at some examples where it's given as data rather than the actual number, and we'll figure out how to get the number from that data.
Oh, right.
So we'll look at examples of those.
Okay, thank you.
You're welcome. All right, so now the big reveal. Now the big reveal. After you've predicted on your own, now you go and you match it up, and we do our final check, and we label our protons. Okay, so we expected a 3 hydrogen singlet around 3.8. Do we have that? A 3 hydrogen singlet at around 3.8. Bam, there it is. Perfect. So we know that this is proton A. This is proton A, type A. All right, do we have a 2 hydrogen triplet around 2.2? Around 2.2, there it is, 2 hydrogen triplet. Perfect, perfect. So that is B. We're confirming that this was B. Do we have a 2 hydrogen sextet around 1.3? Well, look at this. Actually, it's around 1.6 or 7. So it's a little further downfield than we predicted for an ordinary methylene, but does that make sense? Do you see something in our structure that would explain why it's pushed a little further downfield? Yeah, sure. It's got this carbonyl. It's not directly attached to it, but it's just 1 carbon away. So it's going to have some of that inductive effect is going to be affecting it. So that looks totally reasonable for it to be a little higher, right? A little higher than 1.3 because of that carbonyl. And then do we have a 3 hydrogen triplet at 1? A little below 1. Perfect. There's D. All right, so those are the steps we're going to take step by step. And with that systematic approach, it's going to be a lot easier to solve these problems. All right, let's try another one. Any questions about this one? C13, sorry, C13. Can we pick anything out of C13? I think there's one that we can assign right away. We have 5 signals in the C13, numbered 1 through 5. Can you tell me which one is carbon 1? Which one is carbon 1? What's special about carbon 1? Where's it showing up? All the way down at 170. I just covered it up. I can't read it anymore. 170. Which carbon is that? That's the carbonyl. Right? Remember, an ester usually comes a little below. So that's our carbonyl. So even if we didn't have the IR, we would know there's a carbonyl before we started assembling our pieces. Very nice. Who do you think carbon 2 is? Which of these 4 carbons do you think would be carbon 2? Which would you expect to be the furthest downfield? Who's attached to the most electronegative atom? Yep, attached to the oxygen. So this is carbon 2. And probably, again, 3 is probably the one next to the carbonyl, and 4 and 5 probably kind of goes down the order like that, further away from the functional groups. Okay, so we can't make big alpha to oxygen. We can't make every assignment necessarily in the C13, but we could usually get a little data from it. So really our energy is going to be focused on the proton NMR. All right, let's try a second one. Let's try a second one. Okay, C10H14. C10H14. Let's have you work on the IR, labeling the peaks in the IR, and coming up with the degrees of saturation. I'm going to have you work on it for a couple minutes. Try that on your own. And I normally would have you working on groups with this. But when I do breakout sessions, you can't see my screen anymore, and maybe not everyone has this printed out. So I'll have you work on it independently. All right, let's check in. Some of you might already be done with this, but others might still be working on it. But we'll all touch base and see where we are. If you guys want to unmute your microphone so you can kind of shout out some answers, that would make things go a little more smoothly. It's a little sad just talking to an empty computer. I have to admit, but I know it's awkward when you have video and all that. So but if you want to shout out, that'd be great. Or type in the chat. So, okay, tell me about the IR. Do we see anything reading left to right? What's the first thing that jumps out at you? Anything interesting?
SP2CH.
SP2CH, and where do we find that?
Around 3028.
Yeah, so just above it. So even if you can't see the numbers, the only number you need to know is 3000 so that you could see, yes, in fact, I have something above 3000. They can be really, really tiny. That's okay. But yeah, that is going to be a CH stretch. And specifically, it's an sp2 hybridized carbon. So that's the way we're going to label it, is sp2CH. It's an sp2CH bond that's stretching, 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 and the carbon is trigonal planar. All right, and what do we see next?
On the other side is sp3CH.
sp3CH, very good. So we'll make sure we'll label that. We want to get in the habit of marking up our IR, because that's going to be part of your grade, is pointing to the relevant peaks. All right, very good. So we have things just above and just below. And anything else interesting?
Maybe a little before the 1500, that could be a C double bond.
Yeah, so definitely a needle in the haystack. Carbon-carbon double bonds are quite variable in how strong they are. And they're also in that fingerprint region. So notice I didn't talk anything about CC double bonds because sometimes you see them, sometimes you don't, not really something diagnostic. Okay, so for now, we'll leave it at this because there's no carbonyl. We'll see if we can find anything else later. And we might be aromatic. The sp2 could be an aromatic ring. It could be an alkene. We'll see that in just a bit. All right, and then how about the formula? How many DUs did we get?
4 degrees is unsaturation.
I have a 4. Anyone else second that? Anyone else get that? What would the saturated formula be with 10 carbons?
C10H22.
Yeah, so remember that's 2N plus 2. 2N plus 2. So we just compare that to our H14, and we have 8 hydrogens missing. So yeah, I agree. Looks like it's 4 degrees of unsaturation. That's a lot of degrees of unsaturation. A lot of degrees of unsaturation. That it kind of gives us a clue, right? Just FYI, anytime you have 4 or 5 or 6, you know, that means you might have an aromatic ring. That's a really easy way to take care of a lot of that unsaturation all at once. All right, so now let's move to our pieces. For here, it doesn't matter if you start left to right or right to left, any order you want to do it, okay? But we're gonna make a little table here of a list of our pieces. And what we're gonna be focusing in on is this, integration, integration, integration. So what do you think about we'll start right to left a little easier. Okay, so let's start with E. So this 3 hydrogen signal, what's that piece?
CH3.
CH3, so I think I have a methyl group. Peak D, another CH3, 3 hydrogen signal. Peak C tells me it's a CH2. Peak B must be a CH. So what does a CH look like? A CH actually has 1, 2, 3 arms, right? A CH has 3 other groups that are going to be attached to it to get our total of 4. And then tell me about A. Is that a CH5? What's going on there?
It's a ring, maybe? Like a ring?
Yes, and what kind of ring? A special kind of ring. To come all the way down at 7, that means we have a benzene ring. Okay, now again, I know that those of you who are just starting 3150 right now have no idea what it means to be aromatic, and we're not going to talk about it for another like 12 weeks, okay? But the one example of an aromatic ring is a benzene ring, and it's a very special. So it's always a 6-membered ring, and it always has the 3 alternating pi bonds. That's called a benzene ring. And so the aromatic ones, those are the ones that show up around in that region of 7. So what else do I know about this benzene ring? What do I get from that integration? If there's 5 protons on that ring, that means there's just 1 something else attached. Right? Do you see how we can make that? Okay, so the neighbors, remember that the neighbors talk about the splitting, the shape of it. We're not looking at any splitting right now. We're only looking at the integration. The only time we're paying attention to the chemical shift is when it's around 7, because that's a special type of puzzle piece. That's our aromatic ring. So right now we have 5 protons, which means it must be an aromatic monosubstituted benzene ring, right? Because that would give me 1, 2, 3, 4, 5 other positions, all have hydrogens on it. Look good? So those are my pieces. Any other pieces? Any other pieces? How do I know if there's any other pieces? I add this up. Do we have C10H14? 6, 7, 8, 9, 10. Yeah. And the hydrogens are always going to work out because we use those numbers to come up with our pieces. All right, so again, very quick, 5 minutes. 5 minutes, we're ready to assemble. And so how do we start assembling? Pick one of our end pieces, so either one of these methyl groups, and we decide what it's attached to. What are my choices? And again, you could pick either methyl. So let's say this is methyl E. Okay, let's pick one of our methyl groups and let's analyze it. What are your choices? What can it be attached to? Can it be attached to a methyl group? No, because that's bringing two end pieces together and we wouldn't have room for anything else. It could be attached to a CH2. It could be attached to a CH. Could it be attached to the benzene ring? No, that's another end piece, right? So those are my only two choices. It's either attached to the CH2 or it's attached to a CH. How do I decide? How do I decide? Now I look at that splitting pattern. Right? How would you describe this? 1, 2, 3. Right? It's a triplet. It's a triplet. So what does that mean? It must be attached to the CH2. I kind of went in the wrong direction here. Okay, very good. So who's the CH2 that I just attached it to? So I could use one of my CH3s and oh, there's only one CH2. So this must be CH2. Which
C?
letter is that?
C?
It's C, yeah. There's only one CH2 that has the integration of 2, so that's good. So now we look at C and we look at its chemical shift, its splitting pattern, and we decide who else he's attached to.
The one with the one hydrogen, the carbon with the one hydrogen?
So the CH group?
Yeah.
Yeah, I think that's a good guess because that works out with the splitting, but here's an even better, a better point to make is there's only one other thing, one thing it can be attached to because this is an end piece and this is an end piece. So actually we're at the point where there's only one way to assemble this. We have a group here with 3 arms and we have 1, 2, 3 things to attach to it. There's actually only one answer at this point. So every once in a while you might want to step back and say, you know, wait, how close am I to bringing all my pieces together? Okay, so I have this CH, it has the CH2, CH3 attached to it, E and C. And then it has a benzene ring attached to it, and it has another CH3. And that's our solution. Oh, this is a CH2, sorry, a little typo there.
Oh, Dr. Starkey.
Yes.
So the end pieces that you're talking about, you're primarily like determining if it's an end piece by how many arms it has?
Exactly. If it only has one point of attachment. So once you attach, it's like a stopper. Once you attach that, nothing else can get attached. It has no other arms. So that's why you can't just connect 2 end pieces until all your other pieces have been accounted for. So that really narrows down our choices, right?
Yeah, it does. Uh-huh.
Very
Okay.
good. Awesome. All right. I will let you confirm that this is the right answer. One thing, let's just look at B. How would you describe the splitting in B? Notice that it's blown up here so that you could see it a little better. So we have 1, 2, 3, 4, 5, 6. So that's a sextet again. How many neighbors does that mean?
5.
Must have 5 neighbors. So there it is, 2 on this side and 3 over here. All right, so that makes sense. That's very good. And let's just take a quick look at the C13. Let's take a quick look at the C13. How about those carbons 1, 2, and 3, and 4? Which carbons do you think those are, just based on where they are in the spectrum? Right, they're way up here in the hundreds. So when we looked at our C13 big picture, when we look at our C13 big picture, right, in the hundreds, we have our sp2 carbons. So that's where all our aromatic carbons are going to be. Carbonyls are way up here. Okay, so I have 4 aromatic carbons. Does that make sense? If you looked at this and you were to predict for the benzene ring, if you were to predict how many carbon signals you would have, would you come up with 4?
Four carbons on, can you repeat that again?
Do you see
Sorry.
that? So if you were to predict, like there's 6 carbons, right?
Mm-hmm.
But it's not going to give 6 unique signals because we have some symmetry. So just like
Right.
protons can be chemically equivalent and show up as one peak in the proton NMR, carbon's the same thing. So the symmetry here that we have goes like this, right? Through that benzene ring, we can relate the carbons to each other. So these 2 carbons, so let's just say 2 and 3 and 4, we don't know who's who. But if this is carbon 2, then this is also carbon 2. If this is carbon 3, then this is also carbon 3. And this is carbon 4, there's only one of those. Okay, now actually the only assignment I can make definitively is that this one is carbon 1. And I could do that because this is a teeny tiny carbon, teeny tiny signal rather. And what's observed is that in C13, when you have protons on the carbon, it kind of amplifies the signal. So what this is telling me that it has no hydrogens attached. So that tiny one is the one that has the alkyl group attached to it. And then 2 and 3 or 4, again, I don't know, I don't know who's who. But what I wanted to point out is the symmetry. This benzene ring, a monosubstituted benzene ring, only has 4 C13 signals. Very good. All right. All right, let's jump to some other examples. So what if the integration is not given to you? Sometimes it might be given to you as numbers underneath. So let's say this could say like 32 and 35 and 51 or something like that. So sometimes you get numbers underneath and then you have to kind of divide them each by the smallest one and come up with the lowest possible number. Klein has a very nice discussion on how to do that if you need to. What I wanted to show is how you can use these integral trails. So these integral trails are a way of graphically showing you the area under the peak. And what we're paying attention to is simply the height of the integral trail. It started at this level and it ended up at this level. And so we're looking at the height that it climbed. So A is this high, B is this high, and C is this high. Okay, and now again, if we had on paper, what I would do is I would demonstrate how I usually just take a scrap piece of paper and line it up, and I make myself a little scale. And I'll say, okay, well, if A is 1 proton, then this much is 2 protons, right? I make myself a little scale. And then when you line it up to C, you're gonna find out, and you probably see it just by visualizing it. C is not twice as high as A, is it? Right? Do you agree? You can't fit two of these in here, right? It would kind of go all the way up here. So that means A is probably not just 1 proton. Maybe A is 2 protons. So you look at your smallest signal, and maybe it's 1 proton, maybe it's 2 protons. So let's do this. Let's say A is 2 protons, and that means B is also 2 protons. And then if we use that height to be equivalent to 1 proton, then when we divide this up, 1, 2, oh, it looks like C is 3 protons. Okay, so we can use, I mean, you could actually measure it and do millimeters or something and then divide it, but really you could just kind of do it by scaling out, by drawing yourself a little scale on a piece of paper. Okay, so now the other thing to keep in mind is we know how many hydrogens we have that are in the NMR. There's 7 total. So you want to divide those 7 protons up in such a way that it relates to the heights of the peaks, and that's what we've done. This is 2, and this is 2, and this is 3. Then that totals 7, and it makes sense. Okay, so that's how you could use these integral trails. Let's try another one. How about this one? We have 10 hydrogens. We have 10 protons. Why don't you see if you can decide how to break up those 10 protons over these 5 signals. Now notice that the integral trail for A and B and C, the integral trail never had a chance to drop back down to 0. So it kind of just built off each other. So what we do is we just look at before it started with A and when A ended, that is the height that corresponds to A. Signal B starts here and ends here, so that's the height for B. And then C started at this level and ended at this level. So that is the height for C. You see what I mean? Okay, so of those 5 heights, can you see if you can divide them up on how to distribute those 10 protons? I'll give you a minute to try that on your own. And a good idea is to start with the smallest signal and see if it works out. If that signal was 1, does it work out that the others are good multiples of that? Remember, it has to add up to exactly 10 when you're done. All right, so kind of when I look at it, what I see is that A and C look like the same height, and A and C and D all look about the same height. And they're all about twice as big as B. So we'll see if that works out. If we say that B is 1 hydrogen, and then, doubling that, A is 2 hydrogens, C is 2 hydrogens, D is 2 hydrogens, and then how would E look? Maybe breaking it up like that, 1, 2, 3. That looks like it's consistent with the heights. And we have 2, 4, 6, 7, 10. We have 10 total. Very good. All right, so we might have to work to get the integration is what I'm pointing out here. In other cases, like the homework that I'm giving to you, the integration's already given to you. Okay, the integration's already given to you. For the homework, I think it's these 2. I think it's 6 and 7 are the ones that I want you to try on your own for homework. Okay, so let's look at 1 now. What's the next step I could do? There's no IR. So what do I do next? Let's look at the formula. So we know that it's CN H to the 2N plus 2. So our saturated formula is C7. How many hydrogens can 7 carbons hold? You double it, and then there's 2 more. That's the kind of math that I like. I'm sorry, 14, 15. I can't do it while I'm talking. That's the kind of math I like for organic chemistry, right? 2N plus 2. That I didn't do it again. Sorry. 2N is 14 plus 2 is 16. I can't talk and write at the same time, obviously. Okay, but here's the question. What do I do with this bromine atom? Right? We said it's okay to ignore oxygens, but what do we do with the bromine? Let's think about how would you put a bromine on a structure? How does that affect the number of hydrogens on the structure? You would have to take a hydrogen off in order to fit a bromine on, right? They both have exactly 1 arm. They fit perfectly. So what we could do is we can look at this formula and say, you know what? This formula has the same degrees of unsaturation as C7H8 would have. So we're going to take all the halogens that we have and just group them in with our hydrogens, and then we have a much simpler formula to evaluate. So what we're going to do is we're going to compare C7H16 to C7H8. And we're missing 8 hydrogens. So,
Dr. Starkey?
yes, please.
So is it any halogens that are gonna kind of add in with the hydrogens?
Right. Every halogen has exactly one bond and displaced exactly one hydrogen to get there.
Oh, okay.
So we could mentally just swap it back with a hydrogen and evaluate that structure instead, and we would get we get the right answer.
Sure.
Okay, so we have 4 degrees of unsaturation. 4 degrees of unsaturation. That is a lot. All right. So let's come up with our pieces. We don't have too many pieces. What are some of the pieces we have? We have a 3 hydrogen signal. So I have a CH3. That's what peak C is telling me. And how about A and B? CH2, CH2? Careful here. So the only time we're not just simply using the integration is when we're in that region of 7. When we're in that region of 7, what is that? What structural clue does that lead to? Aromatic. We have a benzene ring. Okay, so here's what I'm going to do. I'm going to look collectively at all of the integrations in that area. We have a total of 4 hydrogens in that area. A total of 4 hydrogens. So what piece of the puzzle is that? It's a benzene ring that has 2 things attached to it. 2 things attached to it. So that we'll have a total of 4. And if I do it with the para substitution like this, so it's symmetrical, now I would actually get 2 hydrogens. These 2 hydrogens are equivalent, so it would lead to a 2 hydrogen signal. These 2 hydrogens are equivalent, so that would lead to a 2 hydrogen signal. And what would the splitting pattern be? We could just check that right now, FYI. So if we look at this red proton, what would its splitting pattern be? How many neighbors does it have? It has just 1 neighbor. So it would be a doublet. And what do we have? We actually have a doublet. So that makes sense. Okay, so I'm jumping ahead a little bit because we're running out of time. So I just wanted to kind of confirm that para substitution, that 1,4 substitution makes sense. Okay, so I have a methyl group. I have a disubstituted benzene ring. Any other pieces to my puzzle?
An oxygen?
Yeah, we have to look at our formula.
Bromine.
We have an oxygen, 2 arms, and a Br, 1 arm. Okay, and so the only clue I have on how they're put together is this methyl group. Tell me with the methyl group, is he attached to, he could be attached to the benzene ring directly, or he could be attached to the oxygen. He can't be attached to the bromine because that would be a complete molecule. So was he more consistent with being attached to an oxygen or a benzene ring? How do you decide? We look at our chemical shift. Both of them would give a singlet. Neither of them has any neighboring protons, but we're all the way down near 4. All the way down near 4. What does that mean?
Deshielding.
Very deshielded. And the only thing that will do that is the oxygen atom. So I have a methoxy group, OCH3, on one side of the benzene ring, and I have a bromine on the other. I have a bromine on the other. All right, let's see if we can come up with the pieces for this next one, and then we'll probably be out of time. I'll post the key. I'll post the key to the other problems on this page 2 and 3, so that you can get more practice. In fact, I'll post the key to if I have them for some other ones, 4 and 5. I'll post the key to all the ones other than your homework, so you can get more practice if you want. Okay, how many degrees of unsaturation do we have for C9H10? C9H10, that's compared to C9H20. We have 10 hydrogens missing.
Is it C9H12?
It's C9H. So this is the saturated
Oh, sorry,
formula.
22.
Oh yeah. So it's
Sorry.
18 plus 2.
Oh,
18. Yep.
oh,
Plus
sorry,
2.
I did the math wrong.
Yeah, I know. It's easy to do. So yeah, you could write it out. You can calculate it. So 18 plus 2. So we actually have 5 degrees of unsaturation that we're dealing with here. And so that, again, a lot of unsaturation. Let's see if we can come up with our pieces. I have a CH3. I have a CH3. I have a CH2. I have, oh, this all big mess down here. All in this region, around 7. I have a total of 5 hydrogens in the aromatic region. So how does that correlate to a puzzle piece?
Dye substituted?
Dye substituted, or to come up with
Mono?
5. Yeah, it
Oh,
must be
it's
mono
mono.
substituted, right? So benzene itself has 6 hydrogens. So every group, right, takes away from that. So I have a mono substituted benzene ring. All right. What other pieces do I have? Coming back to our formula, we have an oxygen. And we have another oxygen. And we need 9 carbons. We don't have 9 carbons. We only have 6, 7, 8. So we have a carbon. Oh my gosh, we got a lot of loose ends here. And how about your degrees of unsaturation? We need 5. Do we have 5 in our pieces right now? The benzene ring is only 4. 3 rings and 3 pi bonds in a ring. So we also have a DU. All right, so guess what? A lot of loose ends that can be very nicely tied up by thinking about all 3 of these together. There's a very common functional group that has a carbon and an oxygen and a degree of unsaturation. Can you think of what it is?
Can you please scroll up a little bit?
Oh, I'm sorry, am I off the screen? Is that better?
Thank you.
Sure. So 1 oxygen and 1 carbon and a degree of unsaturation. What's that puzzle piece? I see someone
Carbonyl?
suggested aldehyde. Yeah, but just in more general, we call it a carbonyl. So I don't know what's attached. It might be an aldehyde or a ketone or a ester. It could be anything, but it is very likely a carbonyl. You see carbonyls all over the place. So these are my pieces that I have to put together now. These are the pieces that I have to put together. All right, I'll let you put those together. I don't want to keep you guys late. I'll let you put these together. I'll post the key to these so you have some more practice problems, and you can get some practice with those before you tackle the ones in the homework. I'm happy to discuss the ones in your homework if you get stuck. You're welcome to work with others to work on them as well. But if you want to bring them to office hours, we can work on them together. I'm very happy to do that with you. My goal here is for you to be able to solve NMR problems. So I want you to get them all perfectly correct. So reach out if you need help. And I have educator lectures if you want to step back and do a bigger picture of NMR and see some more practice problems there. But otherwise, you should be set to work on those problems on your own. And we have the safety, the emergency preparedness homework that both of those are on Gradescope where you turn them in. And there will be a little bit of pre-lab work for you to do for the oxidation lab. I'll post that worksheet in the coming days so that you can take a look at that well before we meet up again on Wednesday. All right, questions before we head out? Thank you for your patience. I promise we're not going to be going this long any other Wednesday. So that's good news, because normally with the Chem 3150 lab, we're always going right up until 5:50 and trying to race to get out of there. So that's something that's an advantage to not being in the face-to-face lab this semester, is we're not going to be running late and working so furiously. Okay, so that's it for me. I'll stick around if you have any questions, but otherwise, I'll end the recording and you're welcome to take off. Have a great week. And for some of you, I will see you tomorrow.